Section 6. Data Representation. Introduction. In the previous study session, we explained computer data storage as a technology consisting of computer components and recording media used to retain digital data. Therefore, in this section, we will discuss how data is represented in computer system. We will look at decimal and binary integer numbers representation, hexadecimal numbers representation, conversion from one base to another, fixed point real numbers and floating point real number. Finally, we look at ASCII character code representation. Learning outcomes. When you have studied this session, you should be able to explain how data are represented in computer system, explain decimal, binary, and hexadecimal integer numbers representation, convert from one base number to another, analyze fixed point and floating point real numbers representation, explain ASCII character code representation. Representation of data within the computer. When humans use numeric data, they usually represent the numbers using the decimal system, that is, base 10. Working in decimal numbers requires the ability to differentiate between 10 different states, the digits 0 through 9. For the human brain, this is straightforward and may even be extended to take account of alphabetic information, that is, the characters A to Z and A to Z. Computer systems are built from large numbers of similar electronic circuits. Although it is possible to build electronic circuits which can store and manipulate 10 states, it is easier and cheaper to build electronic switches that may be in one of two states, either on or off. Such circuits can therefore be used to represent binary data base 2 with, for example, binary 1 and 0 being represented by the on and off state respectively. Computer systems internally represent all information, data and instructions in binary form with conversion between binary and human readable forms for input and output. When working in machine code or assembly language, it is sometimes necessary to use binary or some similar number system. Binary numbers tend to be very long and hence it is easy to make mistakes when dealing with such data. In such situations, the hexadecimal base 16 number system is commonly used. It is very easy to convert between binary and hexadecimal. Decimal and binary integer numbers. The table below shows the comparison between the number base and possible state for both decimal and binary numbers. Decimal digit, binary bit, number base, possible state. Decimal and binary integer numbers. The above table shows that a decimal digit can represent one of 10 states, 0 through 9, and a binary bit, a single binary digit, is called a bit, can represent 2 states, 0 or 1. It is possible, however, to represent more states by joining a sequence of digits or bits together, and in such a case, it is assumed that the least significant digit or bit is the rightmost and the most significant is the leftmost. The bits or digits are generally numbered starting with the least significant from 0. An 8-digit decimal number. In the decimal system, the least significant rightmost digit represents units 100, the next tens 101, the next hundreds 102, etc. Therefore, the above 8-digit number can represent values in the range 0, all digits 0, to 9999999, all digits 9. an 8-bit binary number. In the binary system, the least significant rightmost bit represents unit 20, the next 2's 21, the next 4's 22, etc. Therefore, the above 8-bit binary number can represent values in the range 0, all bits 0 to 11111111. Binary, all bits are 1. It is possible to convert between number bases, and 11111111 binary is equivalent to 255 decimal. Larger values can be represented by more bits. For example, a 16-bit binary number can represent 0 to 65535 decimal, and a 32-bit number 0 to 42949967295. Within a computer system, a memory word is built up from a number of bits. Typical word sizes are 8 bits, usually called a byte, 16 bits, 32 bits, or 64 bits. In practice, the majority of modern computer systems use a memory based on bytes of storage, with sequences of bytes being used to store 16, 32, or 64-bit numeric data. Bit 7654321 bit value 2 raised to power 7, 2 raised to power 6, 2 raised to power 5, 2 raised to power 4, 2 raised to power 3, 2 raised to power 2, 2 raised to power 1, and 2 raised to power 0. Binary addition. The following truth tables show all the possible combinations of the addition of 1. 2 bits A and B, 2. 2 bits A and B plus a carry-in from a previous addition. In both cases, the addition results in a sum and a carry-out. The rightmost bits are added using left-hand table above. This results in a sum and a carry bit, which is carried out to be added into the addition of the next 2 bits using the right-hand table above. This addition then results in a sum and a carry-out etc. The majority of modern computer systems store numeric values in sequences of bytes, that is, 8-bit words of storage. A single byte is limited to representing a number in the range 0 to 255 decimal. If the addition of 2 bytes results in a carry-out of bit 7, the result is greater than 255 and an error has occurred. When carrying out integer arithmetic on a computer system, care must be taken to ensure that the results will fit the word size being used. Generally, 16 or 32 bits are used for integer number calculations. Signed binary numbers. Mathematical and scientific calculations require the storage of negative as well as positive integer numbers. To represent a positive or negative number, using the binary system, 1 bit, usually the leftmost bit, is reserved for the sign. A negative number can then be represented in a number of forms, e.g. to represent 10 decimal as an 8-bit signed binary number. Mathematical and scientific calculations require the storage of negative as well as positive integer numbers. To represent a positive or negative number, using the binary system, 1 bit, usually the leftmost bit, is reserved for the sign. A negative number can then be represented in a number of forms, e.g. to represent 10 decimal as an 8-bit signed binary number. A. Signed through magnitude 10001010. B. One's complement 11110101. C. 2's complement 11110110. A. Sign through magnitude form. The leftmost bit holds the sign of the number 0 for positive and 1 for negative, and the other 7 bits represent the magnitude. In the example A, 0001010 is the magnitude equivalent to 10 decimal, and the leftmost bit is 1 to indicate that the value is negative. This system is not commonly used in computer systems because it requires separate addition and subtraction circuits. B. One's complement form. To obtain the negative of a number, each bit of the positive binary value is complemented, that is, O's are replaced with ones and ones with O's. In example B, plus 10 decimal 00001010 binary is complemented to form 10 decimal, that is 111101001 binary. This form is used in some computer systems, e.g. ss6 series, but it has the problem that O can take two forms, plus 0, 0000000, or minus 0, 11111111. C. Two's complement form. To obtain the negative value of a number, the one's complement is obtained and then 1 added, that is, in C, above the value of plus 10 decimal 00001010 is once complemented to obtain 11110101, and then 1 added to obtain 11110110 minus 10 decimal in brackets. The advantage of complemented numbers is that separate addition and subtraction circuits are not required. To subtract a number, its complement is formed a very easy operation, and the result added using the normal adder circuit to the other number. The majority of modern computer systems use two's complement form to represent signed binary numbers. In practice, signed numbers are used for normal arithmetic calculations and unsigned numbers for addresses, e.g. in assembly language programs. Overflow in binary operation. Overflow occurs if the number of bits is too small to store the result of an arithmetic operation. For example, when using 8-bit signed numbers, the binary addition 01101110 plus 00101101 decimal 110 plus 45 would result in the value 10011011 binary. It can be seen that the addition of the two positive numbers has resulted in the incorrect negative value minus 101 decimal. After the computer hardware has carried out an arithmetic operation, it sets condition code bits that indicate if 1. The result was 0, 2. The result was negative, 3. A carry resulted from the operation, or 4. An overflow occurred during the operation. The condition code bits can be used in program control structures and for checking for error conditions. Many high-level language runtime systems automatically check for overflow errors, and special instructions can be used by assembly language programs to text the condition code bits. Hexadecimal numbers. When working in assembly languages, it is often necessary to specify memory addresses and bit patterns. To do this using binary numbers would be cumbersome and error-prone. That is, to represent a 16-bit binary number, 16 zeros and ones would have to be entered. In practice, the hexadecimal base 16 number system is commonly used. 1. It is a very concise way to represent numbers Each hexadecimal digit represents 4 binary bits, and 2. It is easy to convert between binary and hexadecimal. Conversion from one base to another. 1. To convert a binary number to hexadecimal, A. Working from the least significant rightmost bit split the binary number up into groups of 4 bits. B. Using table 6.6, convert each group of 4 bits into the equivalent hexadecimal digit. For example, 00011001110 to 000100111001 is equal to 139E hexadecimal. 2. To convert from hexadecimal to binary, replace each hexadecimal digit with the equivalent 4-bit binary value. 3. Conversion of decimal numbers to binary. To convert a positive decimal integer, the following algorithm starts by generating the least significant binary bit, then the next etc loop next binary bit is equal to decimal underscore value /2, ignoring remainder until decimal underscore value is equal to 0. E.g., convert decimal 38 to binary. Result: 38/2 is equal to 19 remainder 0 gives binary 0, 0. 19/2 is equal to 9 remainder 1 gives binary 1, 10. 9/2 is equal to 4 remainder 1 gives binary 1, 110. 4/2 is equal to 2 remainder 0 gives binary 0, 0110. 2/2 is equal to 1 remainder 0 gives binary 0, 00110. 1/2 is equal to 0 remainder 1 gives binary 1, 100110. To obtain the binary equivalent of a negative decimal number, convert the absolute value to binary, then take the 2's complement. 4. Conversion of binary numbers to decimal. The following algorithm converts a binary number to decimal. Decimal underscore value is equal to 0. Loop starting with the most significant binary bit. Bit underscore value is equal to value of current binary bit. Decimal underscore value is equal to decimal underscore value *2 plus bit underscore value until current bit is the least significant. For example, convert 100110 binary. Remember the least significant bit is bit 0. Bit processed 543210 decimal underscore value bracket 1*2 plus 0 *2 plus 0 *2 plus 1 *2 plus 1 *2 plus 0 is equal to 38. 5. Conversion of decimal numbers to hexadecimal. The following algorithm generates the least significant rightmost hexadecimal digit, then the next digit etc. Loop remainder is equal to remainder of decimal underscore value /16. Next hexadecimal digit is equal to hexadecimal equivalent of remainder decimal underscore value is equal to decimal underscore value /16, ignoring remainder until decimal underscore value is equal to 0. E.g., convert 1567 to hexadecimal. Result: 1567/16 is equal to 97 remainder 15 gives hexadecimal F. Result is F. 97/16 is equal to 6 remainder 1 gives hexadecimal 1. Result 1F. 6/16 is equal to 0 remainder 6 gives hexadecimal 6. 61. Result F. 6. Conversion of hexadecimal numbers to decimal. Decimal underscore value is equal to 0. loop starting with the most significant hexadecimal digit. Digit underscore value is equal to hexadecimal value of current hexadecimal digit. Decimal value is equal to decimal underscore value star 16 plus digit underscore value until current hexadecimal digit is the least significant. For example, convert 61F hexadecimal to decimal. X digit processed to 10. Decimal underscore value 6 stars 16 plus 1 star 16 plus 15 is equal to 1567. Fixed point real numbers. So far, only integer numbers have been considered. Such numbers are useful when calculations on whole number values are required, e.g., for loop control in programs. In practice, however, it is necessary to be able to represent fractional components of numbers as well. These are called real numbers, and one means by which this may be represented is in fixed point form. The following shows a 16-bit binary value in which the whole number part with sign is stored in 8-bit, bit 8 to 15, and the fractional component in 8-bit, bits 0 to 7. For example, decimal 10.75 would be 1010.11 binary. The major limitations of this system of real number representation are that 1. The maximum absolute size of numbers is limited by the number of bits assigned to all the whole number part as with a normal binary integer number. 2. When dealing with small fractional component, accuracy is lost, and very small values cannot be represented at all. That is, the smallest value that can be represented by the above fixed point number is 0.0039065. In practice, these restrictions on fixed point numbers do not make it worthwhile providing the extra software or hardware within the computer system to process. Floating point real numbers. In many scientific and engineering applications, very small or very large numbers have to be represented, e.g., from the sizes of atomic particles to intergalactic distances. In the floating point number system, the real value is represented by a signed fractional component called the mantissa and a signed exponent. For example, decimal floating point numbers using base 10 can be represented mantissa star 10 exponent where 0.1 is equal to mantissa less than 1.0. To maintain accuracy, the absolute value of the mantissa is maintained within the range shown. This process is called normalization, e.g. 6520000.0 will be 0.652 star 107 and minus 0.00000000652 will be minus 0.652 star 10 minus 8. In practice, many printers cannot print superscripts, so the above examples would be printed as follows: 6520000.0 as 0.652E7 and minus 0.000000652 as minus 0.652E minus 8, where the E indicates an exponent of 10. Within computer systems, the fractional component is held as a binary fraction and the exponent is a power of 2 or possibly 16. A typical system may store each floating point number in 32 bits with 24 bits to hold the signed mantissa and 8 bits for the signed exponent. In this case, the accuracy of the mantissa is 23 binary bits, which is equivalent to 6 or 7 decimal figures of accuracy, and the range of the exponent will be minus 128 to plus 127. Greater accuracy can be obtained by using 64-bit storage, in which 53 bits may be used to store the signed mantissa, given 15 to 17 decimal figures of accuracy, and 11 bits for the exponents. Floating point calculations can be carried out using floating point coprocessor chips or emulated in software that uses the integer arithmetic operations of a computer. The advantage of floating point hardware is that it can be several orders of magnitude faster than software emulation, but it requires more complex and expensive hardware. ASCII character code. Table 6.8 lists the ASCII character codes, American Standard Code for Information Interchange, with the columns being the decimal value, the hexadecimal value, then the corresponding character. ASCII is the most widely used character code for data transmission between computers, terminals, and printers. As with all information within the computer system, characters are represented by binary patterns. In the ASCII code, each character is represented by a 7-bit code that is stored 1 character per byte, with bit 7 set to 0 or used as a parity check. The characters below 32 decimal, 20 hexadecimal, are non-printing control characters. These are used to control the action of printers, display screens, communication systems, etc. Important control characters are NUL, null, no action used as a fill or delay character. BEL, bell, rings the keyboard bell or buzzer. BS, backspace, move back 1 character width. HT, horizontal tabulate, move horizontally to next tabulate position. LF, line feed, move page vertically 1 character height. FF, form feed, new page on printer, clear display screen. CR, carriage return, move to start of current line. ESC, escape, used in many systems as a program control character. SP, space, move horizontal by 1 character width. For example, to move a printer or a display screen to a new line position, the character CR carriage return, then LF line feed will be output. In addition, some of the printable characters will depend upon the printer font being used. It is worth noting that the ASCII codes for the numeric characters 0 to 9 and alphabetic characters A to Z and A to Z are arranged in ascending numerical order. This property can be used for 1. Testing if a character is within a range, that is, in the range A to Z. 2. The conversion of numeric decimal data entered at a keyboard into internal binary form. Do not confuse the code for a numeric character with the equivalent numeric binary value, that is, the code for the character 1 is 31 hexadecimal 49 decimal. When a number composed of several digits is read from a keyboard, the character codes are read, turned into the equivalent binary numeric value, and then added to any previous total. The following algorithm reads a decimal number from a keyboard until a non-digit is entered. Number is equal to 0. Read character, loop while character is in the range 0 to 9. Digit underscore value is equal to character minus 0. Number is equal to number star 10 plus digit underscore value. Read character, end loop. In the majority of programming languages, a character code value is specified by enclosing it in quote marks. In the above algorithm, characters are read from the keyboard until a non-digit character is hit. If the character is a digit, say 7 was hit, the ASCII code for 0 is subtracted from it to get the equivalent numeric value digit underscore value. That is, in this case, 30 hexadecimal, the code for 0, will be subtracted from 37 hexadecimal, the code for 7, to give digit underscore value equal to 7. The number entered so far is then multiplied by 10 and the current digit underscore value added. When character information is transmitted over a noisy communications channel, a parity bit can replace bit 7, which is not used in the ASCII code, or be added to make the total character length of 9 bits. Study section summary. In this study section, we learned that 1. Data are represented in computer systems using binary number zeros and ones because electronic switches from which they are built may be in one of two states, either on or off. 2. In practice, the hexadecimal-based 16-number system is commonly used because it is a very concise way to represent numbers. Each hexadecimal digit represents 4 binary bits, and it is easy to convert between binary and hexadecimal. 3. Computer systems store numeric values in sequences of bytes, 32 or 64 bits. 4. The majority of modern computer systems use tools complement form to represent signed binary numbers. 5. Computer systems also use methods like ASCII code to represent non-numeric data. This is the end of study section 6. Thanks for listening.